everybody. Welcome to this recorded version of Lecture 8. So we have two topics to discuss in this lecture. The first one is to finish off Chapter 1 with a few comments about relationships between elementary row operations and other aspects of matrix algebra. So we've seen that elementary row operations are useful when you want to solve a system of linear equations, and we've generally applied them to its augmented matrix in order to describe the solutions. So the comment really here is just that elementary row operations themselves can be interpreted in terms of matrix algebra, and especially as matrix products. And also that they can be used not only to solve systems of linear equations, but also, for example, to calculate inverses of matrix or other objects that you might want to know about in matrix algebra. So first comment is that, as we know, we have three types of elementary row operation. We can multiply a row by a non-zero scalar. That means multiply all the entries in the row by the scalar. We can swap a pair of rows, or we can add a non-zero multiple of one row to another row. And the comment really is just that each of these can be interpreted as a matrix multiplication operation. So let me just, the sort of details of the theorem are stated here with a typo included. So let me correct that typo. This one should be EKK. But rather than going through the steps of this sort of technical statement, let's just look at an example that will show us how this goes. So I'm going to insert a page there. I'll just take an example of a matrix to which we'll apply some elementary row operations. So okay, here's a 3x4 matrix. Let's say let's just make one up. So we'll give ourselves a 3x4 example. So let's put 1, 0, 1, 2 in the first row, 1, 1, 2 minus 1 in the second row, and 2, 4, 0, 1, let's say, in the third row. So that's a 3x4 matrix. And suppose we decide that we want to apply an elementary row operation to it. So suppose, for example, that we decide that we want to multiply the row 3 by 4. I'm not saying that there would be a good reason to do this, but it's an example of an elementary row operation. So the claim is that is the same thing as taking the whole matrix and multiplying it on the left by the almost identity matrix, which has 1, 1 in the first two entries of the diagonal and 4 in the third entry. And certainly if we consider how this operates under the usual processes of matrix multiplication, we can observe that we have the effect of multiplying the third row of this matrix by the scalar 4. So if we look at the first row of this product, it's just 1 times the first row of our matrix, plus 0 times the second row, plus 0 times the third row. So it's just the first row left untouched. Similarly, the 0, 1, 0 in row 2 here gives us back the second row of the matrix that we started with. But the 0, 0, 4 takes 0 times the first row, 0 times the second one, plus 4 times the third one. So it has the effect of multiplying this matrix by 4. This matrix, this 3x3, is an example of what's called an elementary matrix. And an elementary matrix basically is any matrix with the property that multiplying something on the left by it has the same effect as performing some elementary row operation. If you want to try an elementary row operation of a different type, for example, supposing that you want to add a multiple of row 1 to row 3, for example, or something like that. So here's our matrix again. So if we decide we want to replace row 3 of this matrix with row 3 plus row 1, that'll be equivalent to multiplying it on the left by a 3x3 elementary matrix. We're not changing row 1. So the first row of this 3x3 will be the first row of the identity matrix. It'll just pick up the first row of the thing we're multiplying by. We're not changing row 2. We're going to add 2 times row 1, let's say, to row 3. We're not changing row 2, so we take 0, 1, 0 in the second row. So far, we have the rows of the identity matrix. In the third row, we're taking row 3, but to it, we are adding 2 times row 1. And that has the same effect as multiplying the matrix on the left by the matrix whose third row is 2, 0, 1. When we fill in our matrix here, 1, 1, 2 minus 1, 2, 4, 0, 1. And we can observe that when we calculate this product, for each entry in the first row, it just gets hit by this 1, and it just survives exactly as it is. So we get 1, 0, 1, 2. Second row, each entry picks up this 1 in the second position of row 1. This is another so-called elementary matrix. corresponding to a row operation of that third type, where you add a multiple of one row to another row. So the second row is going to survive here again, 1, 1, 2, minus 1. But in the third row, if we look at what's happening to each entry, well, we're picking up the entry itself. This 1 in the lower right corner guarantees that. But we're also picking up 2 times the entry above it in row 1. So in this position in the lower left, for example, we get 1 times this 2 plus this 2 times this 1. So every entry gets twice the entry in row 1 above it added. So we get 2 times 1 plus 2, which is 4 there. We get 2 times 0 plus 4. We get 2 times 1 plus 0. And we get 2 times 2 plus 1 times 1, so 5 in the last entry. So the observation really is just that any elementary row operation that you might like to carry out can be interpreted as multiplying on the left by some square matrix, which sort of quite closely resembles the identity matrix, except for some adjustment that changes the action from just being the identity to performing one of these elementary row operations. So the adjustment might be a change to one of the values on the main diagonal, as in the first example there, if the row operation is multiplying a row by a non-zero constant, or it might be that some row of the matrix has an additional entry in it besides the one on the main diagonal. So this matrix agrees entirely with the identity matrix, except for this lower left entry, this 2. So that means the effect of multiplying any matrix on the left by this one is that you're multiplying it by the identity, except in that row where it has an extra entry, and there you're adding a multiple of another row to the row in question. So in this case, it's row 3 that changes, and it changes by having 2 times row 1 added to it. The third type of elementary matrix, just to mention it, is if we wanted to do the type of row operation which swaps 2 rows. Let's say we want to swap row 2 and row 3. Then the way to achieve that by a left multiplication by a elementary matrix is to take your matrix. Okay, so we want to swap row 2 and row 3 here. So we should multiply the matrix on the left, 0, 1, on the left by something which would put row 3 in the position where row 2 is, and would put the second entries of the second row here into the position where row 3 is. So the first row doesn't change. We should put 1, 0, 0 in row 1 here. We want to pick up the third row and put it into the position of the second row. So we should take 0, 0, 1. And the effect of that in the left multiplication is just that this row picks up the last entry of every column here. So we get the 2, 4, 0, 1 in row 2. And in row 3, then, we should get the entries that are currently in the second row. So instead of taking the identity matrix, we're basically sort of swapping the positions of 2 of the ones in the identity matrix corresponding to the 2 rows that we want to swap. So these are the 3 types of elementary matrix. The first one is corresponding to the row operation of multiplying a row by a constant. The second one to the row operation of adding a multiple of one row to another row. So we have elementary matrices of 3 types. And the third one to the operation of swapping 2 rows. So the observation, I guess, overall is we know that we can use elementary row operations to reduce any matrix to reduced row echelon form. And here we're not even talking about the context necessarily of systems of linear equations. We're just talking about, that any matrix can be reduced to reduced row echelon form by the Gauss-Jordan elimination procedure. So here we're kind of saying that each step in that operation can be interpreted, if we want, as multiplying the matrix on the left by one of these elementary matrices. And the composition of these multiplications amounts to multiplying the original matrix on the left by the product of all these elementary matrices. So the conclusion really is that any matrix can be reduced to reduced row echelon form by multiplying it on the left by a sequence, or if you like, by a product of elementary matrices. So just a couple of remarks here about that on the slide. These 3 types of matrices are referred to as elementary matrices. They're always invertible, and that's relatively straightforward to check. You can basically sort of figure out what the inverse of an elementary matrix would be by figuring out what row operation would reverse the one that it does. And indeed, the inverse of an elementary matrix always also is an elementary matrix. Every elementary row operation can be reversed by another elementary row operation. Okay, so the comment basically is that any matrix can be reduced to reduced row echelon form by multiplying it on the left successively by a sequence of elementary matrices, or by multiplying it on the left by a product of elementary matrices. So we're not going to really talk about this an awful lot. It's not going to be that important for us, but it's something to bear in mind, and it's convenient in certain contexts to think about elementary row operations as actually being matrix products. The second thing that I wanted to say about using Gauss-Jordan elimination in matrix algebra is something that's actually a little bit more important, possibly, and a little bit more useful, maybe, or well, they're both useful, but this one is useful in a quite a direct way. Okay, and the point there is you can use Gauss-Jordan elimination to calculate matrix inverses in a relatively efficient way. So the setup here is that we have some square matrix with entries in some field, so think of the field as being the real numbers or whatever. And if the matrix is invertible, so if it has an inverse, then we can write down the columns of its inverse. So the matrix multiplied by its inverse, of course, would be the identity matrix. So here we have the product of the matrix with its inverse. Here we have the n by n identity matrix. And if we give the names v1, v2 down to vn to the columns of the inverse of A, considered as column vectors with entries in F or whatever it is, then what we are saying is, oops, there's an extraneous A here that shouldn't be there. We're saying that A multiplied by the vector, but by the matrix, whose columns are v1 through vn, and the position is we know what A is maybe, but we don't know what these columns v1 to vn are. We'd like to know what the entries of the inverse of A are. So we're saying that the relationship between A and its inverse is that they multiply together to give us the identity matrix. So in other words, if we take the matrix whose columns are AV1, AV2 down to AVN, that should be the n by n identity matrix. So we don't know what the entries of v1, v2 are, but we know what the entries of the identity matrix are. And so in particular, that tells us that for each I, A multiplied by the ith column of A inverse, which is VI, that's a matrix vector product, and it should be the ith column of the identity matrix, which has 1 in position I and 0s elsewhere. That vector, incidentally, is often referred to as EI, just the vector that has 1 in position I and 0s everywhere else. So if you like, we could say what we're saying here is that the ith column of the inverse of A is a solution of the linear system that says matrix A multiplied by VI is equal to EI, the ith column of the identity matrix. And here, the variables in the system are the unknown entries of VI. Okay, the coefficients are A, we know them. The right-hand side of the equation sorry, the right-hand side of the system is just EI, which has 0s in all positions except the ith position, which is a 1. So the augmented matrix of this system, the system AVI equals EI, has augmented matrix A in the first n columns, and in the last column it has a bunch of 0s, a 1 in position I, and that's it. So essentially, if we kind of take this interpretation of A, here in the right-hand column we have 0, a 1 in position I, and 0 everywhere else. Okay, so in principle, we can apply Gauss-Jordan elimination to solving that system. Because A is invertible, the system should have a unique solution. All variables should be leading variables, and we can calculate the ith column of the inverse of A by reducing this augmented matrix to reduced row echelon form. At that point, we'll have a copy of the n by n identity in the columns corresponding to the variables, the columns corresponding to this appearance of A, and the solution for VI will be written into the right-hand column. So that's fine, and that sort of says that we can interpret each column of the inverse of A as being, in terms of the solution of some system of equations whose coefficient matrix is A and whose right-hand side is one of these columns of the identity matrix, which is fine. So, I mean, so certainly by doing this for each column, you can solve for each of the columns of the inverse of A. That way you can calculate the inverse of A. So one remark about that is all of these columns, all of these right-hand columns in these different versions of this setup for the different columns of the inverse of A, they all have the same coefficient matrix and they only differ in the right-hand columns. So rather than going through the whole process n times, once for each column, we can just write all of the columns together in the right-hand n columns of a n by 2n augmented matrix. So the idea basically is, if you want to find the inverse of this matrix A, so here's a more concrete example, this 3 by 3 example. So suppose you wanted to find its inverse. So to calculate the inverse of A, what we basically said in the last slide was, if you wanted to know the first column of the inverse of A, it would be the unique solution of the system of equations whose augmented matrix is that matrix that I've just circled in green. If you wanted to know the second column, it would be the unique solution of the system of equations which has the same 3 by 3 coefficient matrix, but which has this column in its right-hand side, and so on for each subsequent column. So instead of doing all those things separately and thinking of these as like n separate systems of linear equations that all have to be solved, we can just roll them all in together. They all have the same coefficient matrix, so we can roll in the 3 right-hand sides as 3 separate columns in the right-hand kind of part of this augmented matrix. So this is essentially an augmented matrix for 3 different systems of linear equations. And the sort of added on part of it is the 3 right-hand sides of each of the 3 systems. So essentially we can solve the 3 of them all together by just applying Gauss-Jordan elimination to the entire thing. And when we do, what we expect to find if our matrix is invertible is that we get a leading 1 corresponding to each of the 3 columns of the original A. If that doesn't happen, so if we get 3 zeros in some single row here in the first 3 columns, that would tell us that the matrix was not invertible to begin with. But if the matrix is invertible, we'll end up with a copy of the 3 by 3 identity matrix in the first 3 columns of the reduced row echelon form. And then what is written into the right-hand side, and again, if you're wondering why this is true, go back to the interpretation in terms of columns. The 3 columns of the right-hand side here are the unique solutions to the 3 systems, which have the columns of the inverse of A as their solutions. This first column is the unique solution to the equation A V1 equals 1, 0, 0, which is the original right-hand side here. So basically what's written into the right-hand 3 columns is nothing but the inverse of the original A, which you can easily check by multiplying the A here by this matrix, which turns up in the right-hand side. So this can be understood entirely in terms of our understanding of systems of linear equations, but I guess the point is that it does actually give us some useful methods for calculating matrix inverses. And on that note, let me just mention, I think usually when we teach students in courses in linear algebra about calculating inverses of 3 by 3 matrices, the usual methods that we use is the so-called cofactor method, where you basically go through the 9 separate processes of deleting a row and column from the matrix and writing down the determinant of the 2 by 2 matrix that remains. So there are 9 2 by 2 determinant calculations to do there, and then we rearrange them appropriately and calculate the determinant of the 3 by 3 thing itself and produce an answer for the inverse. And so if you're dealing with 3 by 3 examples, that method is fairly okay. Like, it's not a huge task to calculate 9 2 by 2 determinants and to calculate 1 3 by 3 determinant, which is what you have to do to calculate a 3 by 3 inverse. That method applies generally, but if you want to apply it even to a 4 by 4, there you have to calculate 16 3 by 3 determinants and 1 4 by 4 determinant in order to write down the inverse. And that is not a particularly easy task, and it's not just a bit worse than the 3 by 3 version of it, it's a lot worse, and it just keeps getting worse as it keeps going. So the method of calculating matrix inverses by computing cofactors is really an inefficient method, and not one that not one that anybody would sensibly employ in order to develop computational techniques for calculating matrix inverses. This Gauss-Jordan elimination method, on the other hand, is a lot more efficient in terms of the number of operations that it requires in terms of the size of the original matrix. So it is a widely used method for calculating matrix inverses, and honestly, except for very small matrices, a far more sensible method than the cofactor calculation method. Okay, that is the conclusion of chapter 1. We're going to revisit these topics again and again, because we'll have lots of further reason to come back to concepts of the reduced row echelon forms, elementary row operations, interpretations of the matrix inverse, and so on. But that is the end for now of chapter 1, and it is the end of the discussion of solving systems of linear equations. Okay, so that brings us to chapter 2. Chapter 2 is called Vector Spaces and Linear Transformations, and really chapter 2 is about concepts, and we're going to meet some of the big concepts of linear algebra here, and I hope that you'll have a chance to really kind of think about them and develop a good understanding of them, because they are very much intrinsic to the language of all mathematics. So we're going to start with the word dimension, just by way of introduction to this chapter. And the word dimension is obviously used a lot. It's used in mathematical language, and it's also used in sort of everyday language when we want to describe our environment. So one of the things we'll try to get at in this chapter is, what does the term dimension really mean, at least in vector spaces? So we think of the real number line as being one-dimensional. And what do we mean when we say that? And by contrast, we think of the two-dimensional plane, or 2, as being two-dimensional. So here's a copy of the real number line. It's just a line. And here's a copy of R2. So it has 2 coordinate axes, typically x and y. So there's R2. We're not going to fit much doodling into this slide. And here's a copy of R itself, the real number line. So to say that R is one-dimensional, at least one way of thinking about what that actually means is that in order to specify the position of a point on the number line, we only need to give one number. We can say we're talking about the number 1, or we're talking about the number 24, or minus 48, or whatever it is. And that pinpoints the position of the point that we're talking about on the number line. So if we're in R2, then to specify the position of a point, we need two real numbers, and the usual two that people would choose would be the x and y coordinates. So for example, if I tell you that I am thinking about a real number, or sorry, a point in R2, whose x coordinate is minus 3, for example, then that tells you that my point is somewhere on the line, the vertical line parallel to the y-axis that passes through the point minus 3, 0. So if I tell you kind of only that piece of information, that the x coordinate of my number is minus 3, that tells you something about where my point is. In fact, it rules out very vast swathes of the plane, but it still gives you an infinite amount of options. So the number of possibilities that you still have for my point, after me telling you that its x coordinate is minus 3, is basically a copy of the real number line itself living inside R2. So in order to specify the position of a point in R2, you need two numbers, and the x and y coordinates will be the most typical two options, but they're not the only ones. So for example, you could use as your two numbers the distance from your point to the origin. That would tell you what circle centered at the origin your point is on, but it wouldn't tell you where on the circle it was. So you'd need a second number to tell you, for example, what is the angle that the line joining your point to the origin would make with the positive x-axis, for instance. Okay, you could specify the position of your point relative to some other pair of lines instead of the two coordinate axes. And there might very well, in some particular situation, be a good reason to do that, rather than using the two coordinate axes. But basically, to specify the position of a point in two-dimensional space, you need a pair of numbers, a pair of coordinates. They don't have to be the standard coordinates, but you need two numbers to pin down a point. So I just want to mention, we're talking about vector spaces, and the concept and definition of a vector space was the first section of the lecture notes. So if you haven't had a chance to look at that recently, I kind of suggest maybe it's a good idea to have a look at it as we're getting into chapter 2. And bear in mind that a vector space is an algebraic structure. So it's a system of objects of some kind, mathematical objects. They might be column vectors. They might be points in space. They might be polynomials. They might be functions. They might be matrices. They can be a variety of different things. And the properties that they must have within the vector spaces, it must be possible to add them together to get another thing that's still in the vector space, or to subtract one from another and still be within the vector space. And it must be possible to multiply them by scalars. So somewhere in the picture is a system of numbers, which are referred to as scalars, and it must be possible to multiply elements of our vector space by scalars and to add and subtract them from each other and to still get elements of the vector space as the result in all cases. Okay, so there are a few axioms that have to be satisfied, but they're sensible ones to follow from what I've just been saying, and they're all detailed in the first section of the lecture notes. So the assertion here is that another example of a vector space that is two-dimensional is a space V consisting of all symmetric 2x2 matrices with entries in the real numbers that have trace 0. So let's quickly have a look at that and think about what does this mean. So V, so let's write a little note about V here. So V is the vector space of all 2x2 matrices whose entries are symmetric with entries in the real numbers and trace 0. Okay, so for a matrix to be symmetric means that it's equal to its transpose. So remember, the transpose is the thing that you get by taking the rows of A and writing them as columns. So if A is equal to its own transpose, then A is symmetric. And of course, in order for that to happen, A has to be square. Otherwise, it doesn't even have the same size as its transpose. And for a matrix to have trace 0, so the trace of a matrix, this is a definition that applies to square matrices only. The trace of a square matrix is the sum of the entries on the main diagonal. And that is a number that every square matrix sort of possesses. It's not clear if you at first glance why it's such an important thing. It's obviously a very simple thing that one can easily calculate. If you have a matrix written down and it's squared, you can calculate its trace easily. You just add up the entries on the main diagonal. So one of the interesting things about the trace is that the trace of the matrix A is actually equal to the sum of the eigenvalues of A, and it's a much easier thing to get at and to calculate than the eigenvalues themselves. So if you don't know about eigenvalues, don't worry, but we'll encounter this a bit later, and we'll encounter the trace also. It's a really important gadget when you're dealing with matrices. So, okay, so this V is the vector space consisting of all symmetric 2 by 2 matrices whose entries are real and whose trace is 0. So if a matrix A, B, C, D is in V, okay, so we've just written A, B, C, and D for the entries of this matrix, then in order for the matrix to be symmetric, well, its transpose, this is a 2 by 2 matrix, so its transpose just has A, B in the first column and C, D in the second. So essentially, to go from this matrix to its transpose, we just swap the B and the C, and we have to get the same thing that we started with. So we must have the B is equal to C for symmetry, and that A plus D is equal to 0 for the trace to be 0. So the conclusion is that V is the set of all matrices that look like this. So if our matrix A, B, C, D is in V, then A must be equal to minus D for the trace to be 0. The two entries on the main diagonal must be negatives of each other. We can have a B, and what we have in the lower left must be the same as what we have in the lower right. What we have in the upper right must be the same as what we have in the lower left for the symmetry to hold. So this is so V is a set of all matrices of this form, where A and B are elements of real numbers. So in order to choose an element of V, we have a free choice for the entry in the top left and a free choice for the entry in the top right. Those can be chosen independently of each other. But as soon as we've chosen them, all four entries are determined, because the lower right entry must be the negative of the upper left, because the trace must be 0, and the other two entries must be equal to each other, because the matrix must be symmetric. So we have, again, kind of like choosing an element in R2, we have two free independent choices to make in order to choose a 2 by 2 symmetric matrix of trace 0. And that's why we would say that this set is two-dimensional. Something that I glossed over and didn't really say properly is how we know that this is a vector space. This is a sort of habit that we should get into as well. If it's asserted that something is a vector space, we should confirm that. So we should ask ourselves, if we take two matrices of this type and add them together as 2 by 2 matrices, which we certainly can do we again have a matrix of this type? Do we again have a matrix which is symmetric and which has trace 0? The answer to that is yes, because the transpose of the sum of two matrices is the sum of their transposes. So if each matrix is equal to its own transpose, then their sum will also be equal to its own transpose. And the trace 0 property also survives under addition. If you have if you have any two matrices, the trace of their sum is the sum of their traces. So if they both have trace 0, their sum has trace 0 as well. And also the property of symmetry and the property of having trace 0, both of those are preserved when we multiply by scalars. So V indeed is a vector space. It's a vector space that lives inside the bigger vector space of all 2 by 2 matrices with real entries. And okay, so we still haven't defined what we mean by dimension. But the idea, again, the fact that, in order to pick out an element of V, you basically have two free independent choices to make, one for this element, this entry A, and one for this entry B. But once you've chosen those two, which don't impinge on each other, but they do impinge on the other two entries. So once you've chosen those two, you have no further choices to make anymore. And that sort of is a kind of capturing of what it means for a vector space to have dimension 2, although it's not quite a definition yet. Okay, let me say a word or two about subspaces and make the comment that V here is a subspace of the vector space of all 2 by 2 matrices with entries in the real numbers, which would be a 4-dimensional space, because to write down a 2 by 2 matrix with real entries, you have 4 completely free independent choices to make for the 4 entries. So we're going to come back to this idea of dimension, hoping that this introduction sort of gives an idea of it, but we need to develop a little bit more language and machinery before we can really pin down what we mean by dimension of a vector space. Okay, so here's a definition, and this is really an important one. So the concept of a subspace. So algebraists like to have algebraic structures of different types, like vector spaces and fields and groups and rings. And we like to have kind of subspaces that live inside them, or sub-objects of the same type. So this definition, you'll see it again and again in slightly different contexts. So if V is a vector space over some field, then a subset of V is referred to as a subspace or a vector subspace if, when you just look at this subset, it itself is a vector space over the same field with the same operations of addition and scalar multiplication as V. So the example to think about here, or an example to think about, is the one we just looked at. Within the space of all 2 by 2 real matrices, which includes every 2 by 2 real matrix you could write down, we have the vector subspace consisting of those examples that are symmetric, so equal to their transpose, and have trace 0. So the sum of their 2 diagonal entries is 0. And it is true that if you take 2 elements of that subspace and add them together or multiply them by scalars, you're still inside the subspace. So that's the key property that distinguishes a subspace from just any old subset. So if you change the last definition, the last example, so that the trace was 1 instead of the trace being 0, then you'd no longer have a subspace, because the sum of 2 matrices of trace 1 doesn't have trace 1. And a scalar multiple of a matrix of trace 1 doesn't have trace 1 unless the scalar you're multiplying by is 1. So this idea of a subset of a vector space that is itself a vector space under the same operations is going to be really important for us. And what needs to be checked to confirm that some subset of a vector space is actually a subspace is 2 things. That the subset is closed under the addition of the vector space. That is, that when we take 2 elements of the subset or the subspace and add them together in the vector space, the larger vector space, that we're still within the subspace. So the lingo for that is closed under this operation of addition, which is quite useful to have in your vocabulary. And also that it should be closed under multiplication by scalars. That whenever you take an element of your subset and any scalar at all in your field and multiply the element of your subset by the scalar, that the result of that should still be within the subset. If those 2 properties are satisfied always for all choices of elements in the subset and all choices of scalar, then your subset is a subspace. And we're going to, so this is kind of the first of our definitions in this section. We'll have a few more of them in the next 2 or 3 lectures, and we'll build up to a really kind of robust concept of definition and also of what's known as a basis for a vector space. Okay, that's it for this one. Thank you very much, everybody. See you next time.